you're measuring distances. And distances depend to first order on the Hubble constant, but to higher order on other cosmological parameters as well. So that's how it works.
So what is the redshift?
Of typical lenses are 0.5 and the source are 2 typically. So this one, RX11 is a bit closer, like 0.2, and the redshift is 0.6. But typically the redshifts are of the deflector are around the half, and the source are.
This only means you would probe only up to about 0.5.
No, because you're also sensitive to the distance to the source, and the source is at redshift 2.
2.
Typically, up to 3.
Okay.
So
up to about 2.
Yeah. So it's very hard to find higher redshift.
I know.
Yeah.
So you still only probe afterwards.
Yes. No. Okay, so, all right, so this is great. Now we want to do it for more lenses, and this is what we're doing now. There's 3 more lenses in the works, these 3. And I hope you will see soon results from one of these at least. This one is almost ready.
Is it quasar?
These are quasars lensed by a foreground galaxy. They're always quasars because we're looking for variability, and the variability is typical of quasars.
The first one is a supernova. It's not quasar.
No, it's not supernova. They're all. This
one
one is a quasar as well.
is quasar too.
Yeah. Only the cluster is supernova. That's the only example we know, but we cannot use that for cosmology. Everything else is using quasars. Okay. So now, what is really the future of this? So this is a paper by Linder in 2011 where he showed that, currently we have about 10 lenses with precise time delays. So we think we can do interesting stuff, get to like Hubble constant of 2% or something like that. But what's really the long-term future of this? So Linder did the calculation. Imagine you have, in this case, I think 150 time delays, and you combine that with what you expect from supernova. See, the complementarity that I showed you earlier, where the parameters are almost orthogonal contours in the parameter space, shows up here, where now this is a time variable cosmological constant. This is the present day value, and this is how it varies with time. These are the uncertainties, 1 sigma. And if you combine time delays with supernova and the cosmic microwave background, the area of this ellipse shrinks by a factor of 5. So just adding a few time delays, you're multiplying your knowledge by a huge amount. So it is a very valuable probe of cosmology that can be done for a and I will get back to that, how we can do this. So keep that in mind. So what about dark matter then? We should not neglect this component. Of course, dark energy is exciting, but dark matter is perhaps something that we have a better understanding of. There's a very large number of theoretical models that make clear predictions of dark matter. There's a lot of experiments that are going after dark matter with direct detection. What can we say about dark matter from gravitational lenses? Okay. So the nice thing is that dark matter is sensitive to mass. So these are 2 pictures of simulations of a galaxy in the universe. In this case, this is cold dark matter. You see, one of the features of cold dark matter is that there are all these little halos in the galaxy. Instead, this is a simulation with warm dark matter. In this case, the dark matter particle is not non-relativistic. It has a non-negligible free streaming length, kind of like a thermal relic of a 2 or 3 keV mass. And in this case, what happens is that these particles are able to escape from the small potential wells because they just stream out of them. And so it erases all the scales below a certain mass. And so it's very hard to know the difference between these 2 scenarios if the only thing you have is light. Because light, maybe stars don't form inside these little satellites, and so you have no way to tell whether they don't exist or they're dark. But if you had the ability to see directly the gravity, the gravitational potential, you would immediately be able to tell which one of these 2 universes is the universe we live in. And so that's why we want to use satellites as a probe of dark matter mass. And here mass is in quotes because it's really the free streaming length. predictions of cold dark matter and warm dark matter. Cold dark matter, these are number of halos as a function of mass ratio with respect to the halo. All the cold dark matter models have a lot of subhalos. The warm dark matter has significantly fewer subhalos because you don't form them and then they don't merge with each other to form bigger ones. So the mass function, this is called the mass distribution of these things, turns over eventually like this. So this is a very clear signature. Unfortunately, you cannot see this in the light because these things also tend not to form stars. This is again a comparison of 3 different cold dark matter models and 1 warm dark matter model compared to the data. And you see that it's very hard to distinguish which one is correct. Because you have to know a lot about the detailed physics of star formation to make comparison when the only thing you're doing is counting the luminosity of the satellites. So we can solve this issue with gravitational lensing because gravitational lensing doesn't care about the stars. You don't care whether they're luminous or not, you just measure their mass. And it's interesting because the flux of a gravitationally lensed image is proportional to the second derivative of the potential. The position is proportional to the first derivative of the potential. And the arrival time, as I said before, is proportional to the potential. So we have information about different derivatives of the potential. So we can use that to test the granularity of the mass distribution. Remember, it's kind of like, if you think about Poisson's equation, the second derivative of the potential is the surface mass density. So if we measure how the fluxes of images varies with respect to some expectation, you can tell what is the surface mass of these objects. And the nice thing is the natural scale of the problem is a few milliarc seconds. So we expect to detect signatures of these little satellites if we can measure positions to milliarc second precision and if we can measure flux ratios. Okay, so this is to show an illustration of this. The natural scale is the Einstein radius, the image separation created by a mass of a certain quantity. A massive elliptical galaxy is typically a couple of arc seconds. A star is typically a micro arc second on the sky, so that's why it's called microlensing. And a dwarf satellite is sort of in between at the milliarc second scale. So we need to be able to measure things on milliarc seconds. So, and it's not a subtle effect in terms of flux. So these are known lenses. So look at this. These are 4 images of a quasar. And these 2 images, if the mass distribution were perfectly smooth, they would have exactly the same flux. Instead, this one is 100 times fainter than you expect. These 2, for example, this should be equally bright as the sum of these 2, and it's not. So we see a lot of these anomalies in the flux, but if you look just at the images like this, you never know whether it's due to substructure, dark matter, or it's due to astrophysical noise. It could be due microlensing due to the stars, or maybe there's some dust here that obscures this image. So you need to find ways to clean up your particle physics from the astrophysics. So how do you do this? 10 years ago, Dalal and Kochanek used radio lenses, where the radio flux is basically immune to the sources of astrophysical noise. And using 7 lenses, they showed that the amount of substructure, the fractional mass in satellites, was consistent with the expectation of cold dark matter. However, they only had 7 lenses, so the constraints were not very constraining. So they said, okay, we're consistent with CDM, this is great. But there was not much else they could do because there were very few known radio loud lenses. So to make progress, you need larger samples, and you need to avoid microlensing, or you can use another technique called gravitational imaging. So let's see how we do this. So you have to select a source that is bigger than the Einstein radius of the thing you're looking for, or comparable, and is bigger than the things that are sources of noise. So you need a source that is bigger than the stars. So stars are microseconds, so you need a source that is bigger than microseconds. For those of you that are experts in active galactic nuclei, you need to look like at the narrow ray region or the dusty torus around the world. So you need to look at these regions. And this is what you would see if you were able to look at these regions. So this is the case I showed before. If the anomaly is from substructure, it persists when you look at them in these astrophysics noise-free modes. If the anomaly is for microlensing, for example, where you use these other methods, you should see the flux pop up. So to cut a long story short, we've done this. So this is an image of another lens where we've taken an image with the Keck telescope in Hawaii and behind adaptive optics. And here, this is an image taken with Hubble, this is an image taken with Keck. And in each pixel, we measure the spectrum. And so this is the spectrum at position A. This is the spectrum at position B. So this is flux as a function of wavelength. And you see these emission lines. This is oxygen and this is hydrogen. These emission lines, especially this point 03, the oxygen 3 line, comes from a region that is big enough to be immune from microlensing. So if we measure this flux ratio, we know for sure it cannot be astrophysical noise. And from this simple measurement, we can tell that there has to be a mass concentration around image A that is distributed like this. Most likely is around here, and it has a mass of about 10 to the 8 solar masses. So although we see no evidence of this thing in the light, so it's completely dark, we know from the gravity that there has to be a little concentration of mass near image A. It is about 10 to the 8 solar masses. To give you an idea, 10 to the 8 solar masses is like Fornax, a small satellite of the Milky Way, but we are detecting this at a redshift of a half, just based on its gravity. Yes?
Sorry, can we also, rule out the possibility of having line of sight structure?
No, exactly. We don't know whether this does not have to be in the plane of the lens. There could be stuff along the line of sight. So, and also, to be, for full disclosure, this is the case where we have one satellite. There could be many satellites doing something like this. There could be a population of satellites. So obviously, when you want to do statistics, one has to account for line of sight effects and also multiple perturbance effects. So this is something that needs to be done once the technique has been demonstrated. But this is a demonstration that you can detect these sort of things.
So if you go back,
Yeah.
and you look at this flux ratio, what is
Yeah.
that ratio?
Hmm?
The A and B.
Yeah.
And it's slightly, from the plot, just slightly,
A is like
lower than,
yeah.
than
Yeah.
B.
Yeah.
But what's that ratio?
What's the number?
Yeah. So
I
it gives
don't
you
remember.
10 to the 8.
No, 10 to the 8 is the departure from the expectation. So if it was completely flat, you would expect a certain ratio between these two fluxes, and a certain ratio between these two fluxes. And I don't remember off the top of my head what's the expectation for flux. It's the fact that you see a departure from that. Say the flux should have been 0.7, the flux ratio, and instead we see 0.5. That is the signal.
Like 0.9 or something.
Yeah, but it is not so much the absolute value of the flux. It's the departure from what you would have in the absence of the satellite that reveals the presence of the satellite. Okay, so this image, for example, here is fainter just because that's the lensing configuration. It doesn't have anything to do with the presence of a
question,
satellite.
Of course, is how much is model dependent?
Exactly. So, and this is the kind of stuff that you do when you have a big sample of these objects. Right. And so you can see, for example, here there's a degeneracy. You can have a bigger satellite over here or a smaller satellite over there. So darker is bigger, so you can move it away. But you cannot move infinitely away, otherwise you wouldn't create effect. And you cannot put it here, otherwise you would move this image away. So there's information about the position of this stuff, but with some degeneracy there.
Is there an explanation why it's over there? Not,
I think it's, we
expert
don't know.
verification, right?
No, it's just statistics. If you look at something like this, why is it here, why is it there, what is chance? And you happen to have a quasar here that creates an image here, you will see it. If the quasar image is here, you wouldn't see it. So you just have to play this thing a number of times, play this game for many, many lenses, and you do the statistics of these systems. You cannot explain why an individual system has a satellite there. Well, the only thing you can explain is the chances of this occurring. It's a statistical thing. another technique is this, where you use, instead of using the ratios between the fluxes, you use directed deflection. This is a beautiful example by Simona Vegetti, where there is a group of galaxies, and one of the satellites of the group, this is a luminous satellite, so we know it exists, is right on the arc. And so it's splitting the arc. So just from the splitting, this image separation, we can tell the rest to be a mass there. So even if we've not seen the stars, we will know there's a mass there. And going back to your question, if the satellite here doesn't do any splitting because it's in the wrong position. So here we're lucky that this happens to be right on top of the image. And there are other examples of cases like this. So now you can see this is the sensitivity of this method depends on the resolution. So you can only detect things where the Einstein radius is comparable or bigger than the resolution of your images. So with Hubble, you can detect things of a certain size. If you go to VLA in another configuration, you can detect smaller masses, right? If you go to Keck adaptive optics, you can detect smaller masses. If you go from so on. It depends on the resolution. And so this is Simona Vegetti has been doing for a few years now. This is the first detection she reported about 10 to the 8 solar masses. And these two images here are a bit too far away. And so she showed that there has to be a bump in the gravitational potential here that is pushing these two images far away from each other. And the bump is about 10 to the 8 solar masses. And recently, 2004, she analyzed a sample of 10 systems. And she found this is the abundance of dark matter in subhalos. And this is another parameter, so it doesn't really matter what the parameters are here. The important thing is that her measurement is consistent with cold dark matter, but is not yet precise enough to rule out warm dark matter. Okay? So she shows that there is dark matter, but she cannot show that there is more dark matter than you would expect in a warm dark matter scenario. Part of the reason is that her sensitivity for this experiment was about a few 10 to the 8 solar masses, which is relatively high considering the limits we have on the free streaming length of the dark matter particle. So now this is an old plot from Strigari, but it illustrates the point very well. So the number of subhalos should be going up very rapidly with going to smaller masses. So we think around the Milky Way there are like 100,000 of small subhalos. And the number of luminous ones is really not increasing that rapidly. Even with the latest discoveries from the Dark Energy Survey, they're probably around here. And so what's happening is that there is a big gap here. And typically, people that do galaxy formation and evolution explain this by saying these halos here don't form stars. But of course, the alternative is that these halos don't exist because, say, dark matter is warm. So if they don't exist, then they're not there. And now, at the moment, with strong lensing, we can detect stuff about here when there's not much of a tension between the number of observed subhalos and the number of satellites. But with future things like the TNT or other future instrumentation, we can easily go down to 10 to the 7, when the discrepancy would be orders of magnitude. And I think this is actually currently being done already with the VLA for a small number of objects. Okay. So the future prospects, so now we can study more or less 10 systems. We're in the same sort of numbers that we have for the time delay cosmology of 10 systems. But future surveys will discover thousands of systems. And it will be possible with extremely large telescopes like the 30-meter telescope or other telescopes to do the follow-up and getting this stuff really well measured. So imagine we want to take the next step and do 100 quasars with flux ratios and time delay. How do we do this in practice? And this is how I plan to spend my next 5 years or something. So first you have to find the lenses. And first thing you have to do is carry out large imaging surveys. Fortunately, we don't have to worry about this because people are doing this anyway. So for example, the Dark Energy Survey is doing it. HSC, the Hyper Supreme Camera Survey, is doing this. LSST will eventually do it. Euclid will do it. WFIRST will do it. So everybody seems to be very keen on doing large imaging surveys. And the forecasts are that there would be thousands of lenses to be found in these big surveys. The difficult thing is finding these lenses, and there are, you know, many techniques being developed for finding these lens quasars, including some here by Sherry and her students. And I'll show you some pictures of where this thing will come from: HSC of Subaru, WFIRST, Dark Energy Camera, LSST. And I'll show you now how difficult this is. These are simulations of some of these things are gravitational lenses, and some of these are just pairs of quasars. Some of these are star-forming galaxies, and I have no idea which ones are which. Okay, so these are the images you typically are given by a ground-based survey. And which ones are lenses? So it's difficult, but Adriano Agnello, myself, and these other two gentlemen have been spending a lot of time thinking how about machine learning techniques can be used to identify these things. So, you know, it's classic needle in the haystack problem. You have to find rare objects, and humans are good, but they get bored. So it's very hard to convince humans to look at 100 million images of the sky. But computers, they don't get bored apparently. So
They make mistakes.
they make mistakes. The humans. So, so we're studying these machine learning techniques, and they seem to work. So this is only simulation. In theory, you can have a certain purity, completeness. Then you can decompose the images in principal components and analyze the images to find things that look like lenses. So this is all good, but you remember that, as they say, in theory there's no difference between theory and practice, but in practice there is. So it works very well here in theory, but then when you go in practice, how does it work? Well, luckily we have demonstrated that this method works. This is a paper just appeared on Monthly Notices. And these are the first two lenses we discovered from the Dark Energy Survey. These are images taken from the ground. And now, I don't know why the quality is so bad here. I might have made some mistake in converting this figure, but you clearly see a deflector in between the two quasars. These are spectra of the two quasars showing that they are identical. And this is an image taken with Keck, with adaptive optics. Now, you cannot see it here, but I promise that there is actually a ringer out here. It's very faint, but there's a ringer out there. This is a short image taken with Keck. In 2 hours of Keck, you see a nice, beautiful ring. So we know this method works. We have to work through the entire Dark Energy Survey, and Sherry is working through the Hyper Supreme Camera Survey. So we'll find many more lenses. Okay, so what do we do when we find them? We have to follow them up. Okay, so we cannot do much science just by knowing that there is a lens there. You need high resolution imaging, and you can do this from space or adaptive optics. We need time delays. So for this, you can do dedicated monitoring in the optical radio, or you can wait for LSST. LSST will do that for us. And then you need to do the mass modeling, getting the redshift, stellar velocity dispersion, and so on. So you need to invest time with telescopes to follow up these systems. Unfortunately, this is a very small amount of telescope time. You can imagine of order a few minutes to maybe an hour for this per system. This takes a little longer, and this takes maybe 1 or 2 hours per system. So a few hundred hours you can really do stage 4 dark energy experiment. One of my concerns is where will the high resolution imaging come from? Of course, sooner or later HST will disappear, and we will be very sad. So we cannot trust this to go on forever. What will we do after HST? Euclid LSST would be great for discovery, so it would be easier to recognize these lens quasars, but they're probably not good enough for cosmography, I think. So there's a paper by Xiaolei showing this. WFIRST will probably be good enough for the brighter lenses. This is a simulation with WFIRST. It's comparable to HST. Well, it's not a surprise. WFIRST is like HST, so it should look the same. Adaptive optics, I think, are very promising. At the moment with Keck, we can get down to about 70 millisecond full width of maximum, and there are many improvements underway. We think we can get down to significant almost diffraction limited at 2 microns. And of course, after 2015, I hope we can develop something called the next generation of adaptive optics. This will be laser tomography, many lasers, and you can get down to up to practically diffraction limited at K-band, and you can get large fraction of the sky covered with adaptive optics. So this, and then of course, after 2018, extremely large telescopes like 50-meter telescope and so on, they're all built with the expectation of doing adaptive optics. So they will be capable of doing this very, very well. Okay. So it will take very short amount of time with a big telescope to do this stuff.
Where is this going to be?
Which one?
2018, you said.
After 2018.
Yeah. Where is it going to be?
Where?
Where?
So there's going to be 3 of them. One in Chile. Actually, 2 in Chile.
2 in.
Different parts of Chile. And then one in Hawaii.
Really?
Yes.
Get on Hawaii. I thought that's forbidden.
I mean, of course, this is a complicated topic, but
Yeah.
I think there's a legal procedure that is, so far we have authorized to build in Hawaii. And of course, there's a debate going on about this, but legally, the expectation is that we will be able to build this in. And then, of course, JWST. JWST is 6 meters, diffraction limited beyond 2 microns. So we'll be able about the resolution of HST, and of course will be much more sensitive. So this will be very powerful. So how much telescope time will this need? Maybe about a few hundred hours with HST, 4 nights with next generation adaptive optics, and very short time with TMT, extremely large telescopes. Maybe ALMA will be doing some of this. I think he will. Time delays may come for free in some sense for LSST. There's a question whether they would be accurate enough. I think we'll have to see that. And for the present day surveys, we can use small telescopes like currently being used by Cosmograph and others. There's a project going on to follow up these things with smaller telescopes, so this can be done. And then for redshift of source and deflector, about 2 weeks of CAC or a few days on a 30-meter telescope using with ALMA. And these are all solvable. Of course, I didn't mention here the modeling. One of the big issues is, of course, that this system needs to be modeled. And modeling is being really a very, very, very important and time-consuming component of this. And this is something we should not neglect. And make sure that there's a proper support for doing the modeling part, the part where you transform this data into cosmological insights. Okay, so my conclusions are that the strong gravitational lensing is a cost-effective tool to study the composition of the universe. And we think we can achieve sub-% accuracy on H0 eventually, and improves the figure of merit to level and archaeological experiments by factor of 5 or more. And flux ratios can reach, in principle, 10 to the 7 solar masses as detection limit for these satellites, and thus allow us to rule out or confirm things like warm dark matter. I hope this is feasible in the next 5 years with some effort, starting from this and the other imaging service. So I will stop here and leave.
Thank you very much. Questions?
Thank you for your very nice talk. I wanted to ask you a question. What if in the future we get 1% precision on H0 and it's like 5% far away from the one from Planck, for example?
So Planck, what do you mean by Planck? Planck doesn't really measure the Hubble constant, unless you assume flat.